talk about field epidemiology, and to begin, I also wanted to talk about the alternate title for this talk is why are mathematics and statistics important? They're important because of the skills that you gain from these courses. Algebra, calculus, statistics, probability, logic, they're all extremely important for analysis of any kind, even including here in epidemiology. So we're going to start with the definition. What exactly, or approximately, let's say, what is epidemiology? Well, this is a pretty standard definition that you can find in almost any textbook on epidemiology. It is the study of the distribution and determinants of health-related states and events and populations of interest. Okay? The key words here are distribution and determinants, and this is where mathematics and statistics become extremely important. Okay? How do I measure distribution? How do I find out what the determinants are for whatever disease or condition that I'm trying to study? The purposes of epidemiology is to assess community health, and that's the biggest difference between medicine and epidemiology, which is part of public health. We are really concerned about the health at the community level, okay, not at the individual level. We identify new and emerging diseases and conditions. Okay, that's another one. Monitor and track existing conditions. That's surveillance, okay, a very important part of epidemiological work. A lot of statistics is used here as well. We need to evaluate effectiveness of control measures. Once you devise them, we have to assess them after some time. Lots of statistics here. Develop policies and communicate with the public. Okay. How do you communicate with the public about your findings? Take English and communication classes as well. Okay, so I'm advertising them too because those skills are very important as well.
Dragan, could you speak up a little louder?
Yes, okay. I'm going to come back to this video at the end of the presentation. It's kind of interesting. If you're a science geek, you're going to find this funny. If not, that's okay. We'll come back to that a little later. Field epidemiology is a branch of epidemiology that's focused on urgent public health problems, okay, such as outbreaks. Okay. Outbreaks of infectious diseases or conditions. Okay. That could be poisoning, including food poisoning. That's basically, most of them are infectious diseases that we are focused on. Okay. Could also be exposure to different substances in the environment. Okay. That's also part of this branch of epidemiology. Every epidemiological study has to answer these 5 questions. Okay. First, you have to define what exactly is it that you are looking at. What is your focus? Okay. Next is who. Okay. What part of your population are you interested in studying? What age groups, what genders? Are there any limitations on who are you going to include in your study and that kind of stuff? Where exactly is it happening? Is it national? Is it just located are you focused on a few states? 2, 3 states? Maybe 2, 3 counties in a state? Okay, maybe just one city or town? Okay, so we have to answer the question where, okay, when? When did the problem start? And what's going on? Okay. And why? Okay, that's the most difficult, and that's the most difficult question to answer. Why are we observing what we are observing? Okay. What are the risk factors? How is this disease or condition transmitting? Okay. So there are a lot of unknowns, right, when you start. So in order to describe what epidemiologists do, we have to talk a little bit about probability and odds. Okay? Both of these are measures of likelihood for an event to occur. Okay? probability and odds, they are related, but they're very different. Okay? They tell you the same story, but in a different way. If we can count the number of outcomes, right, in an event, then the probability is just the ratio. It's just the ratio of the number of outcomes in the event divided by the total number of outcomes under consideration. That's usually your sample, okay, that you're looking at. Okay, it's usually expressed as a percentage. You get a decimal, right? You divide, you get a decimal, and multiply by 100 to get a percentage. So sometimes we like to think about this as a relative frequency, okay, or probability. The odds is a little bit different. The numerator, you will notice it's the same. Okay? It's the number of favorable outcomes divided by the number of unfavorable outcomes. So I'm going to give you an example so that you get an idea how different probability and odds are. So if you took, or if you're taking my statistics class, you have seen this experiment before. You're going to draw one card at random, okay, from your standard deck, well-shuffled deck, right? And you're asking, what's the probability of drawing an ace? Any ace, right? There are 4 aces. So I have 4 favorable outcomes and 52, right? 52 total cards that I'm considering, and that's my probability, right? 7.7%. So one can say 7.7% of my deck are aces as a relative frequency. Okay. The odds is a little bit different, right? The numerator is still the same because I have 4 aces, right? 4 aces, but I have 48 cards that are not aces. So those are my unfavorable outcomes. So it'd be 4 out of 48, or 4 to 48, or 1 to 12. Odds are usually expressed as in this fashion, or you can convert it to a decimal as well. The probability of drawing a red card is 50%, right? Half of your deck is comprised of red cards, and that's 26 out of 52, or 50%. Okay? But the odds is 26 to 26. Right? I have 26 favorable and 26 unfavorable outcomes. So we usually say it's 1 to 1, right? Or some people would say 50-50, right? Using the probability here. You have 50-50 chances of drawing a red card, okay, out of that deck. So as I said, both are telling the same story about an event, but in a different way, a slightly different way. We also need to look at some of the basic study designs in epidemiology, which are used in other fields as well. First one is experimental, okay? The so-called randomized clinical trials, okay? Community trials. Studies can also be observational, okay? Like cohort, case control, cross-sectional, static. I'm going to talk a little bit about those in a minute. In epidemiology and field epidemiology, we mostly use observational studies, mostly. So here's the first epidemiological design for a study. It's called cohort. Okay? You select, first of all, you have to know what your population of interest is. Okay? You're going to select a cohort, basically a group of people that you're going to follow through time and see what happens. Some of these studies can be very long. Some of them could be shorter, could be a couple of weeks. Some of them are a few months, some of them are a few years. Okay? It just depends. It depends on what exactly is it that you're focused on. You're going to measure what happens in the future, right? Who gets exposed or unexposed. Okay. And this is a pretty generic terms when I say exposed and unexposed. Okay. I could also refer to a lifestyle, okay, what you're doing every day on a daily basis. That's exposure as well. And then, of course, sometime in the future, we're gonna see who will develop a disease, who won't. These studies are most frequently prospective, i.e. you're looking into the future and see what happens. The members are easily identifiable and accessible. Exposure is usually rare. That's what we would like to focus on. And the good thing about this study design that you can actually watch out for the development of several different diseases or conditions, right? Because you're following people through time into the future. Okay? Those are very reliable study designs. Okay? They tend to be expensive, and they do require time. Okay? And the biggest issue is the loss to follow-up, which creates a bias in your data. Basically, what that means, you can lose people, okay? Especially if your study is very long, like 10 years, for example. That thing is always there. You're going to always lose at least one person. Okay? Usually more than one. But that's why you want to make sure that what you start with, your cohort is large enough so that you can handle that loss to follow-up in the end. Case control studies are a little bit different. We are going to focus on a population of interest. And in this case, we already know who is diseased and who is not. So we have cases and controls. Now we have to go back in time and figure out who was exposed and who was not exposed to a risk factor that I'm focused on, whatever that may be. Usually what we do here is we rely on the data that's collected from the local health care providers, clinics, hospitals, physicians. Okay? When there's an outbreak, for example, in an infectious disease, the state authorities are alerted right away. Okay? The data begins to be collected immediately. Okay? Sometimes even the Center for Disease Control and Prevention gets involved as well. Okay? It depends on the scale of the outbreak. So case control studies are retrospective, so going back in time, right? This is a very good alternative when you cannot easily identify your cohort. Disease or condition has to be rare as usual, but it is not as reliable. Okay? The biggest issue here is the recall bias and selection bias. How do you selection cases and controls? That's the biggest issue, right? You can spend a whole semester talking about these two biases in the design and analysis of case control studies. They're relatively cheap, though, and they're easy to execute, right? And in field epidemiology, that's usually what we do because we don't have enough time to monitor now what's going to happen. We have to act really fast in order to prevent further spread of the disease or infection, whatever that may be. But there are some problems, right? The recall bias, right? We rely on people when they're interviewed by their physician or a nurse. Right? We rely that information that we are given is good, okay? That we can actually perform a data analysis with what we have. The data is electronically transmitted these days, okay? We don't go into the field anymore and collect data, okay, like we used to many years ago. That's why this field is called field epidemiology. You're out in the field collecting data. We now, usually epidemiologists collect the data electronically from the local healthcare providers, physicians, hospitals, whatever. So there are some issues. There are some issues for case control studies as well. Nothing that you do in statistics is perfect. Okay? There are always going to be some issues. So once I get my data, the time then comes to summarize the data in this fashion. It's called the gold standard, and it originated in medical fields. They love this because it's very simple, it's very straightforward. Computer software can actually summarize this data immediately in this format. What you're focused on is the outcome for people where outcome is present and for people where the outcome is absent. And of course, the other variable, the two other categories, who was exposed and who was not. Okay? So this is what we call the gold standard, 2x2 table. Very simple table, looks very simple, in fact. Okay. But you could do so much with this, it's not even, it's amazing how much you can do with this simple summary table of what you have. The two most important measures for risk are the following: the sample risk ratio and the sample odds ratio. And keep in mind the word ratio, okay? It's a fraction. That's going to be very important later on in the comments. Okay. Like, when is the fraction equal to 1? Okay. For the risk ratio, we are looking at probabilities, okay? We're going to calculate the probability for risk in the exposed group, okay, divided by the probability for the particular outcome, right, that I'm focused on in the unexposed group. And those are given by, in the numerator, you're going to have A divided by A plus B. If you look at the table originally, that's your A. So you divide by the total in that row right here, A plus B. Okay. Divided by the probability for the same thing in the unexposed group, which is going to be C divided by C plus D. So it's a complex fraction, which you can simplify or leave it in that way. The odds ratio is a little bit different. This is the ratio of two odds, but it's a similar idea. So in the numerator, I'm going to have the odds for outcome in the exposed group, which is A over B. Remember, the number of favorable outcomes divided by the number of unfavorable outcomes. If you look at, that's your favorable outcomes, right? A divided by unfavorable outcomes, A over B. Okay. And then for the unexposed group, it's just going to be C over D. And that's from that same table, right? If you get that, you can either leave this as a complex fraction. People usually simplify this by cross multiplying, right? We all know how to do that, hopefully, and we get AD divided by BC. So those are the two very important measures. There are many other ones as well, but we're going to just focus on these two today. Now we need to talk a little bit about number one. Okay, number one. If your risk ratio or the odds ratio is equal to 1, there is no association between exposure and disease. Why is that the case? Well, you're basically telling me that the probability for developing my symptoms or disease is the same in both the numerator and the denominator, i.e. exposed group and the unexposed group. Okay, so I cannot really draw a clear conclusion what's happening. My risk for developing disease is the same, basically, in both groups. Does that make sense? There is no difference, okay? When the risk ratio, the odds ratio is more than 1, we usually say we have positive association, right? Usually that means the exposure increases the risk of developing the disease. When the risk ratio, the odds ratio is less than 1, i.e. it's between 0 and 1, then the risk for developing the disease will be reduced. And this is more of interest in prevention efforts, community interventions, development of medications, vaccines, and that kind of stuff, right? That's usually when you would hope that your risk ratio and the odds ratio is less than 1, right? In order to prove that your new vaccine is effective, right, in fighting the diseases and that kind of stuff. So there are 3 possibilities to watch out for, right? When it's greater than 1, less than 1, and when it's actually equal to 1. And remember why 1 is important here, because we are talking about the ratio, right? A fraction, right? Okay. And you remember, right, when a fraction is equal to 1, that means that there is no difference between the numerator and the denominator, right? They're the same. Very basic idea, right, from elementary algebra, but a very powerful idea, right, when you start applying that simple idea to a setting such as this. The risk ratio is used mostly in cohort studies, and it's easier to interpret because you are comparing 2 probabilities. Okay, 2 probabilities or risks. The odds ratio is used in both cohort and case control studies, but it's a little bit more difficult to interpret, right? I'm going to see what I mean in a minute. So here's an example, right? This is very typical. By the way, there is a case of alfalfa food poisoning almost every year. You just don't hear about it because it's not a major epidemic or anything like that. But this is kind of interesting. So we know Local health authorities have notified us about an outbreak. Okay. We received some data, and we are going to summarize the data in this fashion. We're going to look at two categories here: infection present and infection absent, against people who consumed alfalfa sprouts and those who did not. Does everybody know how alfalfa sprouts look like?
No.
Google it, right? It's not my favorite vegetable, but it's there, right? Okay. So we're going to calculate the risk ratio and the odds ratio in both cases. Remember, for the risk ratio, what do we need? We need 25 divided by 42 in the numerator. Right? That's the risk for infection in the exposed group. And divide that by the probability, right here, probability, right, for the risk in the unexposed group, right? And here we go, right? We have the ratio of two probabilities, right? 0.59524 approximately divided by 0.10. Okay. That gives me a really nice number of 5.95. 5.95. We'll see what that means in a minute. And it says right here, therefore, based on the sample, right, those who consumed alfalfa sprouts are 5.95 times more likely, okay, to be infected with salmonella than those who did not consume sprouts. The odds ratio is a little bit different. Remember, you were supposed to cross-multiply 25 times 45 divided by 5 times 17. It's just a cross-multiplication in that table. And we get about 13.24. 13.24. Therefore, based on the sample, the odds. Now I'm comparing two odds. Okay. The odds for infection in those who consumed alfalfa sprouts is 13.24 times the odds for infection in those who did not. And what's interesting to observe here is that the odds ratio usually overestimates the overall risk. Okay. The risk ratio is always better, it's a better measure, but there are problems with the risk ratio because you cannot always use that, right? If you have a case control study, you cannot use the risk ratio. There are good reasons for it. I'm not going to go into that today. So what do these numbers tell us? They tell us that there is a strong association between consumption, right, alfalfa sprouts, that's my exposure, okay. That's how I measure exposure, and salmonella infection. Now these are just statistics, right? They're based on sample data. So usually as a statistician or epidemiologist, we're not happy with that. We need a little bit more information. So what are we going to do? Well, we're going to try to estimate these numbers in general population. That's what we call the approach of confidence intervals, right? With the most common confidence level of 95%. 95%. That's the most commonly used confidence level. So we would like to get an estimate, a range for these measures of risk in the whole population, okay? In the whole population. And what are we going to be looking for? We are going to be looking for that number 1, okay? I do not want to see that number 1 inside the confidence interval. I'm going to see an example of that, okay? So this is how these confidence limits look like. Okay? It's a little bit scary when you first look at it. There's logarithms in there. There's exponential stuff in there. There's SE, which is the standard deviation for your estimator. And you plug all that stuff in, you calculate, you suffer through it, and you can get your limits. Or you can use an online calculator. I just wanted to talk a little bit about the logarithm, why it's really needed here. We usually want to use the normal distribution or the bell-shaped distribution in our approximations, such as confidence interval. And what we do, we try to see if the logarithm will give us that normal distribution. The risk ratio as is not a normally distributed variable, whatever that means. Basically, it is not bell-shaped. If I were to graph its distribution, it would not look like a bell-shaped distribution. Okay? That's extremely important in statistics, the normal curve. Okay? normal curve. You're going to see that if you take and when you take your statistics class, how important that normal distribution really is. So what we do, we apply the natural logarithm. And then we hope we can apply some other functions to it as well, by the way, not just the natural logarithm. This one is the best one if it works. And then, of course, you have to show, yeah, I do have normal distribution now. That requires some heavy-duty mathematics to prove that you have, that your variable actually behaves as a normally distributed variable. Okay, that's not easy to show. Okay. Similarly, for the odds ratio, it's very, very similar. The formula is a little bit different here, and that's okay. I'm not going to spend too much time talking about this because actually to derive this formula does take calculus and mathematical analysis. It's a little bit, it's very technical, let's put it that way. Very, very technical. I'm also going to show you how to enter data into this online epidemiological calculator, which is free, it's online, it's available to everybody and anybody who's interested. I'm going to come back. I'm going to come back to that at the very end and show you how to do this. So what I did, I entered the numbers that I had into this calculator, and I got my limits. Remember, the risk ratio was 5.952, and here are my limits. Okay. About 2.5 up to 14.18, thereabouts. Therefore, in the general population, now I can approximate the range, right? I can see that the risk is anywhere between 2.5 and 14.8 when I compare exposed group to the unexposed group. Okay? I'm pretty happy because one, that bad number, 1, is not included in this confidence interval. The basic idea in statistics, if this range is too wide for you, increase the sample size if you have the time. Okay? Remember, field epidemiology is focused on urgent public health issues and problems, right? So sometimes you don't have time to get more data into your sample. Okay? But that's the basic idea, right? If you have time, that's what we do. For the odds ratio, right? Remember the odds ratio was 1324, and this is where we get our confidence limits. Okay. So in the general population, the odds for infection in those who ate alfalfa sprouts are anywhere between 4.36 and 40.18 times the odds for infection for those who did not consume alfalfa sprouts. Here's another interesting example. Okay. I have another set of values. The number's a little bit different. And I'm going to calculate the risk ratio. The risk ratio is 1.75. And this is where statisticians and epidemiologists get really concerned, okay, when your odds ratio or risk ratio starts with a 1 or even 2. That could be bad news. Bad news in the sense that you don't have a clear result yet. Okay? You need to investigate this even further. What's going to happen? When I plug in the numbers, these numbers, okay, into my online calculator, I get the confidence interval of 0.68 up to 4.517. What's the issue? The issue is that it is plausible that the population risk ratio is equal to 1, okay, which tells me right away, well, you know, I have 50-50 chances of getting infected by consuming alfalfa sprouts, meaning I'm not there yet, okay, to say, yeah, you need to start recalling, you know, alfalfa sprouts from this particular market, wherever that is. Remember when we talked about the 3 possibilities. One part of your confidence interval tells you what? Tells you that the risk is reduced when you actually consume these sprouts, okay? On the other hand, right, if you move above 1, it's telling you that the risk is increased if you eat these sprouts. Okay? So which one is it? I have two possibilities. On one end, the risk is reduced. Right? Those are the values below 1. And on the other end, the risk is increased. Okay? It's a logical contradiction, right? And this is where we say, well, something else needs to be done. Maybe we are looking at the wrong risk factor. Maybe it wasn't alfalfa sprouts. Maybe it was something else. So what's next? Next is stratification. Maybe I need to start looking at the numbers. If I have the data, right? It all depends on what kind of data you have. Maybe I need to split my data set into two parts and compare to different counties, okay? If that's what's happening. I'm going to fill in the blanks in here with you see the question marks. And then I can compare the risk ratios and the odds ratio. I can just calculate them separately for each group and see what's going on. These stratifications can occur in many different shapes and forms, right? I can look at two different counties. I can further stratify according to age group. If I'm suspecting that this infection has something to do with a particular age group, okay, or age groups, okay, it doesn't matter. Okay, I can split that up. Maybe I need to stratify even more, right, according to gender. Okay, so I may end up comparing 8 different 2x2 tables. Okay. So things can get really, really messy, But we do have technology, right, that will help us analyze what's going on at each level. Maybe I have data for the 3 cities, right? Maybe I need to split that up in this way. Maybe I need to look at some different kind of risk factors. Maybe I need to add chicken to this list at the very end. Who knows, right? So the possibilities are infinite, but I have to have the right data in order for me to be able to do this. Okay. That's usually when the local healthcare providers collect the data, they really ask a lot of questions. Okay. Those questions are very important because the answers that you give, they will determine the data set in the end, okay, that people will analyze. Okay. That's why it's very important that if you ever get into that situation, where you get food poisoning and it's serious, that you kind of remember what you did the last couple of days. And answer as truthfully as you can. If you don't remember, you don't remember. You just say, I don't know, I don't remember. That's okay too. Some people don't remember. That's what we talked about, the recall bias, right, earlier. We talked about the case control study. Even though these techniques were developed in the biomedical sciences, these now can be used in many other fields, and they're becoming more and more popular, especially in psychology and sociology, in marketing, in finance, in management, you name it, economics, education. I see these kind of procedures now in many different fields because they do quantify your relationship between different variables, which is very important. Very, very important. Marketing people love this stuff because they need to know which marketing techniques will be more useful between different segments of the population. That's extremely important. So here's an example from sociology that I found in one of my books, and we're looking at single people, those who were never married and those who were divorced, and whether they like to avoid or not avoid social gatherings and social activities in general. You as a social scientist perhaps want to look at that, right, for whatever reason, right? That's important to you as a social scientist, and that's what you do. Okay. If it's a case control study, risk ratio cannot be calculated here, but the odds ratio will do, and when we cross multiply, right, the numbers right in the table, when you cross multiply, you get 4.032, and the associated confidence interval is 1.964 all the way up to a little over 8. So now I can tell which group of single people are more likely to regularly avoid social activities and which one is not. Okay. So this can be used in many different settings, right? All that you're really dealing with are categorical variables. You have to have frequencies. You have to have frequencies in your table summarized somehow. You have a survey, right? You give out a survey to people, and they fill them out, and then you can fill in the blanks with these numbers, right? And from that point on, you can do a lot of different things. So let's go back to the calculator so that I'll show you how easy it is to use it. So here's the calculator that's available online. It's free for anybody's use. Okay, you don't have to pay. There's no fee to use it. Right? It's there for everybody to use. And there's a lot of things you can do here. One of these days, when you take a serious course in statistics, right? This may become useful, right? But anyway. Okay, so let's enter the data. So we're going to click on Enter Data here. And the table is already set up in the right way. We have 25 here. What else do we have? 17. We have 5 and 45. The grand total, remember the very first table, right? We had 92 people. And I'm just entering the same numbers into this table. Now, what's interesting about this is that you, as a researcher, you have to know when you click on Calculate that you're using the right results depending on what setting you're in. Okay, you're going to see this in a minute. I'm going to press on the calculator here. By the way, if I have stratified data, I can just add more levels of measurement here. So I'm just going to click on Calculate here. This is what I get. Chi-square is that's okay. Talk about that. Here's the first one, the risk ratio. Okay, the computer got the same number that we got, 5.9. What is it? 5.952, and the confidence interval. Right? Yeah, this is based on Taylor series. Okay, that's a concept from calculus, heavy-duty mathematics that's needed in order to actually get those formulas to work properly. There are other things that you can look at. You can look at the risk in the exposed group. Okay, that's the probability of developing symptoms or getting infected in the exposed group. You can look at the overall risk, the risk difference. The risk difference is just the difference between the risk in the two groups. And notice what happens here. This is not valid for case control studies, right? As we said earlier, I cannot use this in case. There are some reasons for that. It's a little bit beyond the scope of what we need to talk about. If we can use the odds ratios, oh, that's okay, right? Remember, it was 13.24. Okay, and there's my confidence limits. So it's pretty easy to use, right? As long as you have your data, okay, that you can enter. Quickly. And then you can notify, once you do your research and you find out the results, you can notify the local health officials, this is it. We need to pull out this particular food item off the shelves so that we can stop this spread. Okay. After that, it usually goes pretty fast, identifying the particular brand of whatever food item you want to focus on. Can easily pull that off the shelves. Okay, that's one thing. And now the I close this. I need to look at the video quickly here.
And there's been an experiment which I think reflects pretty well the characteristic of the profession. And I'd like to tell you about this experiment because it allows you also to situate yourself, with respect to epidemiology. This experiment was the following. It was, a researcher thought, how can we define epidemiology? Well, epidemiology is what epidemiologists do. So imagine the following experiment. He took a room with a surgical table, and he put a can of sardine on the table. And he asked a neurosurgeon, a pathologist, and an epidemiologist to come. And the experiment was very simple. They had to go into the room, do whatever they wanted, but they had to come out with a report. So the neurosurgeon went first, stayed 2 minutes, came out. He had written can of sardine on his paper, and the box of sardine was very nicely opened. There was not a drop of oil on the table, and he didn't care about looking at the sardines themselves. Then goes the pathologist, stays half an hour, comes out, he's full of oil everywhere. The can is roughly open, very strangely. There are bits of sardine all over the table and oil. And he has a 2-page report. This was a metal can, and I opened it according to the procedure of so-and-so. There were 6 sardines. I opened them all. There was nothing pathological, and I think it was, safflower oil or something like that, sunflower. So he gives his report. Then goes the epidemiologist. The epidemiologist stays 8 hours. So the guy outside was starting to get worried. After 8 hours, the epidemiologist opened the door. He looked exhausted. So immediately the guy looks at the table and sees the can of sardine untouched. But the epidemiologist had a 20-page report on how to estimate the number of sardines in the box without opening it.
Okay, so that's basically the message, right? If you want to be a pathologist, get ready to get your hands really dirty. But if you want to be a statistician, epidemiologist, right? It's all clean work. You're dealing with data. Hopefully reliable data, but it's very clean. It's a very clean job. Any questions that you may have?
So what's the magic number to cause a recall? The FDA,
Usually anything about 2.5 or something.
about 2.5?
5. Usually, I mean, it depends on your sample size and everything.
So what's your history with epidemiology?
Well, since I got into statistics teaching here at Western, I was looking for another degree, and then I got interested in this because it was very closely related to statistics and stuff like that. And I realized, well, it's not that difficult if you can think mathematically and statistically. It's basically applied statistics. Or they could be very mathematical too. You can use differential equations to study diseases and that kind of stuff. So you can either do it mathematically or statistically or both.